Okay everybody, welcome. Get your green pens out. This is a walkthrough of your Paper 2 mock. Okay, question number 1. The Earth's atmosphere contains several gases. Figure 1 shows the relative amounts of gases thought to be in the Earth's early atmosphere, and then it says that it was mostly carbon dioxide with a small amount of oxygen, a small amount of nitrogen and a large amount of water vapour. It says the amount of water vapour in today's atmosphere is much less than the amount in the Earth's early atmosphere. Explain why the amount of water vapour in the atmosphere has decreased. Well, you need to know that water vapour is water in its gas form, and that it's gone down because the oceans formed. And so the 2 marks for the answer is to say that the water vapour condensed to form the oceans. So the water vapour condensed, that's the key word that you need, condensed to form the oceans. And that would get you the 2 marks. Okay, part B. The apparatus shown in figure 2 is used to find the percent of oxygen in dry air. And it says syringe A contains 50 centimetres of dry air and syringe B contains no air. Now what they're going to do is they're going to pass the air in syringe A over some hot copper, and the copper is going to absorb the oxygen from the air and make copper oxide. And it says the copper in the glass tube is heated strongly. The air in the apparatus is passed backwards and forwards over the copper until all of the oxygen is removed. The following results were obtained. Well, the initial volume of the air was 50 centimetres cubed. The final volume in the air was 40 centimetres cubed. Calculate the percentage oxygen. Now, you should know roughly that the percentage oxygen in air is 20%. Air is 20% oxygen. 20% oxygen and approximately 80% nitrogen. That's the information. So you're looking at 20%. Well, the change in volume is 10 centimetres cubed, and it's 10 out of 50. So the percentage of oxygen is 10 divided by 50 times 100, which equals 20%. The second part of that question says at the end of the experiment the apparatus and its contents are allowed to cool before the final volume of gas is measured. The apparatus and its contents must be allowed to cool because, well, the answer is C. The gas has expanded when it's hot. You've got to allow it to cool because the volume of gas must be measured at a set temperature because the volume of gas changes with temperature. Part C says the Earth's earliest rocks contained iron sulfide and no iron oxide. Later rocks contained iron oxide as well as iron sulfide. Explain what happened to allow this change to occur. Well, what happened from the early atmosphere to the current atmosphere is that the amount of oxygen increased due to photosynthesis from plants using carbon dioxide and making oxygen. The evidence is that that oxygen is included in the rocks to form iron oxide, and the oxygen reacts with iron to make iron oxide. So early rocks only contain iron and no iron oxide, and later rocks contain iron oxide. So the 2 marks for saying 1, the amount of oxygen in the atmosphere increased, and number 2, the O2 reacted with iron to form iron oxide. And it would be okay to say that the iron in the rocks was oxidized, but as long as you've got that idea that there was a chemical reaction between the iron in the rocks and the oxygen in the air to form iron oxide. Question number 2. A chlorine atom contains 17 electrons, 18 neutrons and 17 protons. State the mass number of this chlorine atom. The problem there is that it's a bit of a trick question. If you look chlorine up on your periodic table, you look at the mass number or the relative atomic mass, it will be 35.5, which is an average for all chlorine atoms. This particular chlorine atom has 18 neutrons and 17 protons, which you add them together, that gives you the mass of that particular atom, which is 35. So the answer is 35. Give the electronic configuration of this chlorine atom. Well, the key there is the electronic configuration. That's your 2,8,8, and just write it out like that with the numbers in it. Well, it contains 17 protons, which is 2,8,7, and of course because it contains 17 electrons, those numbers should add up to 17, which they do. 2 and 8 is 10 plus 7 is 17. Describe what you would see if damp blue litmus paper is placed into chlorine gas. This is a test for chlorine gas, and normally with a gas test it's 2 marks. 1 mark for the test, which in this case is add damp blue litmus paper, but with chlorine there are 2 things that you see, so essentially it's a 3-mark question, but they've told you what to do. Add damp blue litmus paper, and the blue litmus paper turns red and is then bleached. So the litmus turns red for 1 mark and is then bleached. If you put turns white, that would be fine, but the 2 marks for saying that it turns red and that is then bleached. Part C says chlorine exists as a diatomic molecules. In a molecule, 2 chlorine atoms are joined by a covalent bond. Describe what is meant by a covalent bond. Now this is one of your definitions, and the definition of a covalent bond is that it is a shared pair of electrons. And that gets you the 2 marks because you put down that it's shared and a pair of electrons. Now, there were lots and lots of really good ideas that were incorrect, and that's because you were telling me what a covalent bond is. It's a strong bond between 2 non-metals where the electrons are shared. You'd have got 1 mark for that because you said the electrons are shared. But the key thing is that in a covalent bond, I've got a shared pair of electrons, a pair of electrons between them, one of which comes from one chlorine atom, one of which comes from the other chlorine atom, and it's a shared pair of electrons between the 2 atoms. And it was literally, you got 1 mark for shared electrons, 1 mark for a pair. The second bit, explain why chlorine is a gas rather than a liquid at room temperature. Now, things are gases because they have low boiling points, so they've already reached their boiling point and they've boiled and they are gases. So you've got 1 mark for saying that it has a low boiling point. Now, there are a number of ways that you could get the other mark, and you have to recognise the structure of chlorine gas. Cl2 consists of a covalently bonded molecule, but between the molecules you have weak intermolecular forces. Weak intermolecular forces between the molecules, and those forces are easily overcome. So you got 1 mark for saying weak intermolecular forces are easily overcome by heat. So they boil at a low temperature. Now, I forget how many times I say this, but in terms of structure all bonds are strong bonds. Ionic bonds are strong, covalent bonds are strong, metallic bonds are strong. The only weak forces are intermolecular forces. So anything that has a low boiling point is going to have weak intermolecular forces. And that comes up time and time again. So just try and remember it. Part D says when the gas hydrogen chloride is dissolved in water, solution form, and blue litmus paper dipped in the solution turns red, state why this litmus paper turns red. And the answer is the solution is acidic. And that would have got you the mark. The solution is acidic. And the reason that it's acidic is that hydrogen chloride splits up into H plus and Cl minus, and it's the H plus which makes it an acidic solution. Question number 3 is about group 1 metals, and the first part is a empirical formula calculation. It says sodium metal tarnishes in air to form a layer of sodium oxide on its surface. 0.92 grams of sodium combined with 0.32 grams of oxygen in this oxide. Calculate the empirical formula. You must show your working. Now you could probably guess that the empirical formula between sodium and oxygen is Na2O, and we're going to do a calculation which proves that. I've got sodium in my first column, I've got oxygen in my second column. I want to work out the number of moles, so I write down the grams and divide them by the rams. 0.92, 0.32, and it's divided by the ram of sodium, which is 23, and the ram of oxygen, which is 16. It's not 32 because oxygen goes around in pairs. For empirical formula calculations, it's grams over rams. And then I'll write down the numbers that I've got, which is 0.04 and 0.02. Now that is a ratio of obviously 2 to 1. So I've got Na2O, Na2O, and that agrees with a central formula for sodium oxide. Part B, sodium reacts with water to form sodium hydroxide and hydrogen. Complete the balancing of the equation for this reaction and add the state symbols for each substance. Well, the first thing is balancing, I guess, and it's 2 lots of sodium. 2 lots of sodium react with 2 lots of water to give 2 lots of sodium hydroxide and 1 lot of hydrogen. That's the only way that you can balance it to get. Now you got 2 out of the 3 marks for getting the balancing numbers, and the last mark was for getting the state symbols. Sodium is a solid. Water is always a liquid, not AQ, and that's an L. Sodium hydroxide is AQ, and hydrogen is a gas. And if you got all of that, you got the 3 marks. In an experiment, equal-sized pieces of sodium are added to separate samples of water. A flame is produced only with potassium because potassium is the most reactive metal. That was quite a straightforward 1 mark there. Part D says, explains in terms of electronic configurations the increase in reactivity from lithium to sodium potassium. So it increases as you go down the group. So the answer, there's only 2 marks for this, and the answer is as you go down the group, the atoms become larger and the electron, which you're trying to lose, is further from the nucleus, and therefore it's less well held by the nucleus and is easier to lose. And that really, you've got to understand that the reactivity of group 1 metals comes from the metal forming the metal ion and an electron, and that's how they react. And so the easier it is to lose an electron, the more reactive they are. As you go down the group, the atoms are bigger, the electrons are further from the nucleus, and that electron is easier to lose. Question number 4 is about alcohols, and it's actually based on a core practical that you did using spirit burners and burning a series of alcohols. And it says a student investigates how much heat energy is released when a known mass of ethanol is burned. The apparatus is set up in figure 3, and then it gives a bit of a method. You take a known volume of water, put it in a can, record the temperature at the start, burn some ethanol, heat up the water and put the flame out and record the final temperature. And so you've got the mass of the fuel burnt and the temperature rise. And it says the theoretical temperature rise for burning a given mass of ethanol is 82.4 degrees C. In the experiment, the actual temperature rise for burning this mass of ethanol was only 34.8 degrees C. One reason why the temperature rise is less than expected is that the ethanol does not burn completely. Give a reason why, even if the ethanol burns completely, the actual temperature rise is much less than the theoretical value. This core practical, and I emphasised this with my group when we did it, they love to ask you evaluation type questions because it's not a very good practical. You don't get a value near the theoretical value of the energy in the fuel, and that is because of heat loss. And the answer here, any form of heat loss, so heat escapes, heat doesn't transfer to the water, heat heats up the surroundings. So any of those would be a good answer. Heat loss to surroundings would be a good answer there. Part 2, if you got part 1 right, then obviously part 2 says explain how the method described above could be improved to give a temperature rise closer to the theoretical value. Obviously, you need to explain, so you need to give one method that you could reduce heat loss and then explain why that reduces heat loss. So you could put add a lid to the beaker to stop heat transferring to the air. Now there are another number of things that you could have said. You could have said that you could use a draft shield to stop the heat blowing away from the beaker. You can't really say. The beaker in the question is made from a conductor, a good conductor of heat anyway, so you can't really say change the material of the beaker, but you could say anything that says improving the amount of heat that goes into the water by reducing heat loss, and obviously adding a lid or stopping the heat from escaping are the two main things. Part 3, it says the amount of heat energy used to raise the temperature of water by 34.8 degrees C can be calculated heat energy times 210 times the temperature rise. Calculate the amount of heat energy used. This was a simple calculation. They give you the temperature rise, which is 34.8. You've then got to multiply that by 210, and that gives you a value of 7308, and really that was a very simple 2 marks. Part B, it says propanol and butanol are both members of the same homologous series as ethanol. Propanol and butanol could be burned in the apparatus. Give 3 reasons why ethanol, propanol and butanol are members of the same homologous series. This is something that hopefully you've learnt. 3 reasons why the homologous series are the same. I'm going to give the 3 what I think are the simplest ones. They have the same functional group. In this case, the functional group is an OH. So they're all alcohols, and alcohols contain an OH group, and all alcohols will contain the same functional group. They have the same general
formula, and you will have learnt CnH2n plus 2 for alcohols, but for an alkane, for an alcohol, they are CnH2n plus 1 and then a OH. Now you don't need to have that, but I've just put that in, but as long as you had the same general formula. And then you can say something about their reactivity. Now the key thing about, they will react differently, but they have a similar reactivity. So they show a trend in their reactivity. So I think you've got to say they have a similar reactivity, similar chemical reactivity, or they show similar reactions, or they also show a trend in their physical properties. And the final thing that I didn't say, another way that you could get it, was you could say that they have the same general formula and they vary by CH2 units. So each alcohol is CH2 different from the other ones. Now it's not good enough to say that they're just 1 carbon longer, each one is 1 carbon longer. You need to say that they vary by CH2. So that was 1, 2, 3, 4, 5 ways that you could have said it, and any 3 of those 5 would get you the 3 marks. Part C, ethanol can oxidize when exposed to air to produce ethanoic acid and water. Propanol can also oxidize in similar reaction when exposed to air. Write a word equation for the reaction of propanol oxidizes when it is exposed to air. Well, propanol is going to make propanoic acid and water, so it's propanol plus oxygen, propanol plus oxygen goes to give propanoic acid. Plus water, and that would get you 2 marks. And the last one, what is the formula of the functional group in carboxylic acids? Carboxylic acids are COOH, and it was 1 mark for getting that. Question number 5 says an oxygen atom contains 8 electrons, 8 neutrons and 8 protons. State the mass number of this oxygen atom. Well, again, the mass number is the number of neutrons plus the number of protons. 8 plus 8 is 16, so it's going to have a mass number of 16. Give the electronic configuration of this oxygen atom, where you can get to 16 by 2,8 gives you 10, and it's going to have 6 electrons in its outer shell, which puts it in group 6, which agrees with what we know. Describe a test to show that the gas is oxygen. Oxygen gas relights a glowing splint. Now you don't have to say anything about collect the oxygen, you just need those facts. Oxygen gas relights, and that's what you get 1 mark for. Glowing splint, so add a glowing splint is the test. The positive confirmation is that it relights. Always with a gas test you've got your test and you've got your result of your test. Moving on. Oxygen, a gas at room temperature. Explain why oxygen has a low boiling point. This is very similar to the question that we had before. It says there that it has a low boiling point, but again, oxygen goes around as O2, and an oxygen molecule has strong covalent bonds holding the oxygen atoms together, but between oxygen molecules you have weak intermolecular forces. And so when oxygen boils, the intermolecular forces are overcome. So you need to say, explain why oxygen has a low boiling point. Oxygen molecules are held together by weak intermolecular forces which are overcome by a small amount of heat energy. And that will get you your 2 marks. Part D, sodium reacts with oxygen to form sodium oxide, which is an ionic compound. Describe what is meant by an ionic bond. Again, this is a definition. You just need to learn these. And an ionic bond, there's lots of good things that you can say about forming a regular array of positive and negative ions held together by strong ionic bonds. But what is an ionic bond? The ionic bond is the electrostatic attraction between positive and negative ions, and that's what gets you the mark. So it is the electrostatic. What that means, electrostatic, positive and negative charges, essentially. The electrostatic attraction between positive and negative ions. And electrostatic attraction gets you 1 mark, and the idea that it contains positive and negative ions gets you the 2nd mark. Which the following is a typical property of ionic compounds where all bonds are strong. Ionic bonds are strong, covalent bonds are strong, metallic bonds are strong. In an ionic compound, you've only got strong electrostatic attractions, strong ionic bonds. Therefore, they're going to have high melting and high boiling points. So I look down the list, and high melting points is there. So D is going to be that one. Question number 6 is all about crude oil. It says crude oil can be separated into useful fractions by fractional distillation. Figure 7 shows fractional distillation column and the fractions produced when a sample of crude oil is distilled. The properties of these fractions vary from the top of the column to the bottom of the column. Which of the following is a trend in the property of the fractions attained from the top of the column to those obtained from the bottom? The average number of carbon atoms in the molecule present decreases. It increases as you go down. The age of ignition increases. Well, it doesn't. It decreases. The boiling point decreases. No, the boiling point increase. The viscosities increase. That is the correct answer. And viscosity is how thick the substance is. So high viscosity down the bottom, bitumen, the stuff that you use to make tarmac from, has a high viscosity because it's very thick. Most substances in crude oil are alkanes. Which of the following is the general formula of an alkane? For every carbon, you have 2 hydrogens, and then you've got an extra 2, 1 on each end. So it's CnH2n plus 2. So the answer is going to be D. Part 2 says explain why alkanes are described as hydrocarbons. Well, they contain hydrogen and carbon only, and that's a very easy 2 marks. They contain hydrogen and carbon. And you could say atoms or elements. I'll say atoms. But the key word there is only. They only contain hydrogen and carbon, and that will get you the 2 marks. Part C says figure 8 shows a graph of the boiling points of some alkanes against the number of carbon atoms in 1 molecule of each alkane. And then it says explain the pattern shown by this graph. Well, the command word there is explain. if you get asked to explain a graph, you get 1 mark for describe the pattern and the 2nd mark for the science explanation which explains the pattern. So the pattern is the greater the number of carbons, the higher the boiling point, and you got 1 mark out of the 2 for that. So the greater the number of carbons, the greater the boiling point. So that's describe the trend, and then to account for that you need to remember that these are molecules, and carbon, doesn't matter how many carbons, but each one of these carbon molecules exists as a molecular structure, and they are held together by covalent bonds inside the molecules. Yes, the carbons are held by covalent bonds, but between the molecules you've got intermolecular forces. Now the key thing is, as the carbon chains get bigger, the intermolecular forces between the molecules gets bigger, and therefore the boiling point increases. So the greater the number of carbons, the bigger the intermolecular forces between molecules, and therefore the higher the boiling point. Part D says when crude oil is separated into fractions, the amount of each fraction obtained rarely matches the demand for that fraction. Figure 9 shows the relative amounts of the 6 fractions present in crude oil and the relative demand for each of these fractions. And the question is, cracking is used to match the relative amount of a fraction of crude oil to the demand for that fraction. Use the information in figure 9 to give the name of the fraction that is most likely to be cracked. Cracking can turn long-chain hydrocarbons into short-chain hydrocarbons. So which long-chain hydrocarbon is the more of it than we need? And that is fuel oil, because fuel oil is a long-chain hydrocarbon that is a reasonable demand for it, but there's a very big supply. There's a large amount of it. And if you can crack that into a shorter chain hydrocarbon, they would make better fuels. So the answer is fuel oil. Now, part 2 was quite badly answered, and I just want to go through this. And it says, in a cracking reaction, the reactants are heated to form products. The reaction is endothermic. On the axis provided, draw a reaction profile of this reaction. Label the energy of the reactants, the energy of the products, and the activation energy of the reaction. Now, energy profile diagrams show energy up the side against progress of reaction along the x-axis, and they've given you those axes. Now it says that the reaction is endothermic, and in an endothermic reaction the reaction takes in energy, so your reactants need to be at a low energy, so here I could put reactants, and your products are at a higher energy, and the system will absorb energy, and that energy change is the energy change that is taken in, and therefore the surroundings cool down. Now you don't go there directly, you go via an activated state, so the activation energy is up there. And what I've shown then is I go from reactants to products via a state up here which has higher energy than the products. Now still the total energy that is taken in is this part here, but the activation energy is actually going to be all the way from there up to there. So I draw that on, and this is the activation energy, and this is the energy taken in during reaction. Now you've got 3 marks. You've got 1 mark for the energy of the reactants, 1 mark for the energy of the products, and 1 mark for marking on the activation energy. Now part 3 says dodecane can be cracked to form useful products. Complete the equation for the cracking of dodecane by filling in the formula of the single molecule needed to balance the equation. Well, if I just do it by carbons, I've got 12 carbons on this side. I've got 3 lots of 2, which is 6. So I'm going to have C6, and then my H's, I've got 26 on this side. 3 4s are 12, so 26 minus 12 gives me H14. Now, just as a check, I can check I've got a long chain alkane, that gives me a shorter chain alkane and an alkene, which I know is correct because this is CnH2n plus 2, so that's my short chain alkane. Question 7 was another question that was poorly answered, and it's about the halogen displacement reactions, and it says describe what is seen when chlorine water is added to potassium bromide. Now, chlorine water is a very light green colour, but actually you didn't get any marks for saying light green. The key thing is that you recognised that potassium bromide is colourless. Now, the rule there is that the halogens are only coloured when they go in pairs, when they go around in pairs. So Br2, I2, Cl2 all have a colour associated with them: orange, purple, green. But that's only when they are the halogens. When they're a halide ion, so bromide there is colourless. So sodium chloride, salt, will be colourless. Now, if you add chlorine water to potassium bromide, you get a displacement reaction. Chlorine is more reactive than bromine, so it's going to steal the metal from the potassium bromide, and it's going to make potassium chloride, which is going to be coloured, and it's going to kick out bromine, Br2, which is orange. So the colour change that you see is that the solution will go from colourless potassium bromide to brown bromine. So the solution will turn from colourless, and that was 1 mark, to brown stroke orange as bromine, Br2, is produced. Now, the next part of the question is a little bit sneaky because it actually gives you a symbol equation for the reaction in the first part. So if you were unsure about the first part, if you would have read on, you should have realised the reaction with that happening. It says chlorine reacts with potassium bromide to form potassium chloride and bromine. So it tells you down here what is made. In this reaction, chlorine forms chloride ions. So I've got chlorine turn into chloride. In this reaction, chlorine has been reduced. Explain using the equation how you know that chlorine has been reduced. Well, there are lots of ways that you can do this, but essentially chlorine goes to chloride ions, and you could write out a half equation for that. So I've got Cl2 goes to give 2Cl minus, and that is going to be, I'm going to have to add 2 electrons, so it's plus 2E minus there. Now chlorine gains 2 electrons to become chloride, and that is the reason why it's reduced, because reduction is gain. So chlorine gains an electron to become a chloride ion. And the 2 marks were for saying chlorine gains an electron for 1 mark, and to make a chloride ion for the 2nd mark. Now the last part, write a half equation for the formation of bromine from bromide ions. Many of you got this round the wrong way actually. It says formation of bromine from bromide ions. So I'm going to start off with bromide ions, Br minus. I'm going to make bromine, Br2. Now I've got to get rid of that negative charge, and I'm going to do that by adding an electron on this side. And the key thing is I've got 2 bromine atoms here, so I need 2 lots of Br minus, and that's going to give me 2 electrons. So it's 2 Br minus goes to give Br2 plus 2 electrons. Part C says write a reaction. Aluminium reacts with chlorine to form aluminium chloride. Write a balanced equation for this reaction. Well, you weren't given any of the symbols, so aluminium is just Al. Chlorine goes around in pairs, Cl2. You got 1 mark for getting those 2 species correct. You got the 2nd mark for getting the formula of aluminium chloride correct. Now aluminium is in group 3, so it forms 3 plus ions. Chlorine is in group 7, so it forms 1 minus ions. If you do the crossover rule with Al3 Cl1, you get AlCl3. So the formula for aluminium chloride has to be AlCl3. So your 2nd mark was for getting that, and the 3rd mark was for balancing it. If I've got 2 chlorines on this side and 3 chlorines on that side, I need 6 as a common denominator, so I need 3 lots of that and 2 lots of that. That balances my chlorines. I then just need to balance the aluminium, so I put a 2 in front of my aluminium there, and that gives me my 3 marks. Part D was really quite simple. It says a solid ionic compound is dissolved in water to form a solution. Describe a simple experiment to show that charged particles are present in this solution. Well, the charged particles are ions, and the ions move in solution, and then electrons flow around the circuit. So if charged particles are moving, then electrons will flow in a circuit, and this is the electrolysis circuit. So what you need to do is take solution in a beaker and add 2 electrodes. That gets you your 1st mark. Connect the electrodes to a battery or power supply. That's your 2nd mark, and obviously when you turn the power supply on, then a current is going to flow through the circuit, and then you need to be able to measure that current in the circuit. So check current in circuit using, so you could put a bulb in the circuit and the bulb will light up, or a bulb or ammeter. You could put an ammeter in series in the circuit, and that will tell you what current is flowing. Question number 8 says sodium has atomic number of 11. Which line in the table shows the correct number of protons, neutrons, electrons in a positively charged sodium ion? Well, if it's positively charged, it's lost an electron. It would have had 11 electrons. It's going to have 10 electrons, 11 protons, and there will only be one that is there. So the only one that has 10 electrons and 11 protons is D. So the answer must be D. Part B says fluorine has the electronic structure 2,7. Fluorine gas exists as diatomic molecules. In each molecule of fluorine, 2 fluorine atoms are joined by a covalent bond. Draw a dot cross diagram to show the electrons of the molecule of F2 show outer electrons only. So here it has 7 electrons in its outer shell, so I've got F with 7 electrons, 1, 2, 3, 4, 5, 6, 7, another F, this time with dots, 1, 2, 3, 4, 5, 6, 7. So there I've got my dot cross diagram showing the covalent bond is the shared pair of electrons between the two. Part C says sodium reacts with fluorine to form sodium fluoride, NaF. Complete a balanced equation for this reaction. Well, sodium reacts with fluorine. The key thing there is that you need to get F2. And then to balance that, I've got 2 fluorines on this side, I've got 2 fluorines on that side, so it's going to be 2 NaF. That was pretty simple to get 2 marks. Right, part D says sodium fluoride is an ionic compound. That's really important. If I could see inside sodium fluoride, I would see positive and negative ions in a regular array, looking something like this, where the sodium is the positive, the fluorine is the negative, and if it was solid, they would be ions in a fixed lattice. Now it says, describe how a sodium atom and a fluoride atom interact to form a sodium ion and a fluoride ion. Well, sodium atom has 1 electron in its outer shell. Fluorine is in group 7. It has 1 space in its outer shell. Sodium gives its electron to fluorine. Sodium becomes positive and fluorine becomes negative. So the 2 marks were for saying an electron is transferred from sodium to fluorine. So sodium has 1 electron in its outer shell, which is transferred to fluorine to form Na plus and F minus, and both of the atoms are stable because they've both got a full outer shell. The next part, explain why sodium fluoride is able to conduct electricity when it is molten but not when it is solid. Now you need that picture in your mind of sodium fluoride. That is this ionic lattice when it is solid. Now when it's molten or liquid, that breaks up and the ions become free to move. So you need to say when solid, the ions are in a fixed position, but when molten or dissolved in solution, they are free to move and carry charge. So the charge carriers in a molten or solution of an ionic compound are ions. The ions are free to move, not delocalized electrons. Question 9 is all about rates of reaction. It says the rate of reaction between magnesium ribbon and dilute hydrochloric acid at room temperature is investigated. The apparatus used is shown in figure 11. The volume of hydrogen gas given off was measured at regular intervals for the reaction. It then gives a graph. It then gives a graph of the volume of hydrogen produced against the time, which is there. It says, state a change that can be made to the apparatus in figure 11 to measure the gas volume more accurately, the volumes of gas more accurately. Well, you could use a gas syringe instead of collecting it through water. Or you could use a taller measuring cylinder with smaller divisions on it, or a burette. So taller, thinner measuring cylinder, or a burette upturned, which was a bit of a tricky answer actually, and not many people actually got that one. For part 3 on the next page, you were asked to draw the graph if you use powdered magnesium instead of magnesium ribbon. And the key thing here is the reaction rate is quicker, but it produces the same amount of hydrogen in the end. So the rate of reaction is quicker, but the extent of the reaction is the same. And that on a graph would look like a steeper curve, but that finishes in the same place. So that would be the line for powdered magnesium instead of magnesium ribbon. Part 2 says a tangent has been drawn to the line on the graph in figure 12. Calculate the rate of reaction at this point. Well, the rate of the reaction is the gradient of that line, and you calculate the gradient by the change in y, dy over dx, the change in y over the change in x, and the change in volume at y equals 43 minus 15 over 60 minus 0 over 60. So that gives you a value of 28 over 60, which is equal to 0.47. Now it allowed any value between 0.44 to 0.52, depending on how you took your measurements off the graph, but it should be more or less 0.5, 0.47, and that's centimetres cubed per second. That's the number of centimetres cubed that it produces per second. Part 3 says, on the graph in figure 12, draw the line you would expect to obtain if the magnesium in the experiment was replaced with an equal mass of powdered magnesium. All other conditions are kept the same. So in other words, they've changed from magnesium ribbon to powdered magnesium, but they've kept the same amount of magnesium. That means that you're going to get the same amount of hydrogen produced, but it's going to be produced more quickly. So what I've done is I've drawn the line on the previous page, and you get a mark for drawing that. If we move on, part B says the balanced equation for this reaction is Mg plus 2HCl goes to give MgCl2 plus H2. In another experiment, 0.1 moles of hydrochloric acid will react with 0.1 grams of magnesium ribbon. Calculate the number of moles of magnesium in the 0.1 sample of the magnesium ribbon. Well, that's relatively straightforward. Moles equals grams over, this case it's RAM of magnesium, so it's going to be 0.1 grams divided by 24, which equals 0.0042, or 4.2 times 10 to the minus 3 moles. Part 2 says, in a further experiment, 0.5 moles of hydrochloric acid were mixed with 0.5 moles of magnesium. Use the equation to show that in this experiment the magnesium is in excess. Well, from the balanced equation at the top, the moles of magnesium 2HCl is 1 mole to 2 moles. So I need 2 moles of HCl for every 1 mole of magnesium. Well, it says here I've got half a mole and half a mole. So I would need 1 mole of hydrochloric acid to every half a mole of magnesium. So it says use the equation to show that in this experiment the magnesium is in excess. So I think what I need to show is for my experiment the Mg to HCl, if I had 0.5 moles of HCl, I would actually need 0.25 moles of magnesium, and that is the ratio, which implies that the Mg is in excess, and I think that that shows that that is the case. Right, part C was the first of the 6-mark questions in this paper. It says, 2 substances A and B each form a colourless solution. If the solutions are mixed in a beaker, A and B react to form a coloured product. The rate of reaction between A and B can be investigated by placing the beaker containing the mixture on a cross on a piece of paper and timing how long it takes for enough coloured product to be produced to make the cross invisible when viewed from above through the solution. Now, this is an experiment that you did for a core practical. You measured the rate of a precipitation reaction, and it's an inverse relationship. The quicker that the cross disappears, the faster the rate of reaction. So the shorter the time, the faster the rate of reaction. And it then gives you a number of experiments. You've done 3 experiments where the concentration of A is varied, the temperature is varied, and you measure the time taken for the reaction to happen. Now, it says use the results of these experiments to explain in terms of the behaviour of the particles the effect of changing the temperature and the effect of changing the concentration of A in solution on the rate of this reaction. Now you got 6 marks for this, and I split those 6 marks up into 3 separate areas. The first thing was explain what happens to the particles in the reaction when it happens, and that is collision theory. So state collision theory and why reactions happen. Then state the effect of changing the concentration for 2 marks. And then for another 2 marks, state the effect of changing the temperature. And that's how the 6 marks are divided up into the mark scheme. And we're going to have a look at each of those sections in turn. So the first thing that you need to include if you're answering a question about how the behaviour of particles affect reaction rate is you need to describe the theory of collision theory, and this is what this is. This is collision theory. And collision theory says that reactions occur when particles collide with enough energy, and that energy is the activation energy. So you had to say, first of all, that particles collide with greater than or equal to the activation energy for the reaction to happen. And many of you missed this first bit. You went straight into describing the results, and that's where you've lost your marks. And it says reaction rates are increased when the energy of collisions is increased or the frequency of collisions is increased. So reactions go faster because particles heat each other with more energy or more often. So frequency collision or greater energy of collisions. The 2 factors in the reaction that have changed were temperature and concentration. And then we're going to go on to look at those two in detail once we know that reactions happen because particles collide with enough energy. So the next thing to do is to describe the effect of temperature. Effect of temperature on rate of reaction. So if we have a look at the results, we can see the difference between experiment 1 and experiment 2. We have doubled the temperature of the reaction, but the concentration has stayed the same. So if we're studying the effect of temperature on rate of reaction, we need to say that experiment 2 was carried out at twice the temperature, but the concentration was kept the same. Now, between those two reactions, if we increase the temperature, then the particles will move faster, they'll have higher kinetic energy. So there are more frequent collisions, but there are also more energetic collisions. So increasing the temperature has two effects. It means that the particles collide more often, and they also collide with more energy. So therefore you're going to have more collisions with the activation energy, and therefore your rate of reaction is going to go faster. Now, because of those two effects, because of the effect of more energetic collisions and more collisions, then you're going to have a large effect on the rate of reaction. And in fact, doubling the temperature has effect of quadrupling the rate of reaction because the time is decreased by a factor of 4. So in summary, experiment 2 goes 4 times as fast as experiment 1 when the temperature is doubled, because you get more energetic collisions, you get more frequent collisions, therefore you're going to have more particles with greater than the activation energy, and the reaction will go faster. So the last 2 marks were for saying the effect of concentration on rate of reaction, and here we're looking at the difference between experiment 2 and experiment 3, and we've kept the temperature the same, but what we've done is we've increased the concentration by a factor of 4, and that increases the rate of reaction. It decreases the time by a factor of 4, so it increases the rate of reaction by a factor of 4. Now, the reason for that is that as you increase the concentration, you get more particles in the same volume, therefore you're going to get more frequent collisions. It's just a single effect, more frequent collisions, so therefore you're going to have a greater number of collisions with energy greater than the activation energy, more frequent successful collisions, therefore you're going to have an increased rate of reaction. But it is actually just a linear relationship with concentration, that if you increase the concentration, if you double the concentration, you double the rate of reaction. You don't get that double whammy that you get with temperature. Now, you needed to say all of those things in a really well structured answer to get your full 6 marks. Question 10, the first part is a bond energy calculation, and it says hydrogen reacts with oxygen to form steam. Then it gives you a balanced equation, it gives you some bond energies, and it says calculate the energy change for the reaction when 2 moles of hydrogen gas react with 1 mole of oxygen gas to give 2 moles of steam. Well, that's what's given in the equation anyway. So 1 mole of oxygen and 2 moles of water. So in other words, it's calculate the energy for that reaction. Now, all you need to know is energy equals breaking minus making, So breaking minus making. So I need the energy required to break all the bonds in the reactants and the energy required to make all the bonds in the product. Now, they've been a little bit sneaky because they haven't drawn out the molecules for you. They've just written the formula. Now, you may find it easier to work from a diagram of the molecules involved. So you've got two lots of H2, where H2 is HH, and I've got two lots of them, plus O2. O2 is O double bond O, and that goes to give two lots of H2O, OH, H, OH, H. So in breaking all the bonds in my reactants, I'm breaking two HH bonds and one O double bond O bond, and making the bonds in my products, I'm making four OH bonds. So breaking equals 2 times HH and 1 times O double bond O. 2 times HH is 2 times 4, 3, 5. 100 is 500. If I add all that lot up together, I get 1370. You'll just have to ignore my telephone. I apologise about that. So making equals 4 times OH, 4 times 460, which equals 1840. So I've got breaking minus making, 1370 minus 1840. That gives me a value of minus 470 kilojoules per mole, and that it is a combustion reaction. Hydrogen burns in oxygen, and therefore you would expect the value to be exothermic, and the value of minus 470 will get you 4 marks. The second part, part B, is the second 6-mark question, and it says a student is provided with unlabelled samples of 3 liquids. The 3 liquids are known to be hexane, so it's an alkane, hexene is an alkene, and butanoic acid is a carboxylic acid. Aqueous solutions of carboxylic acid contain hydrogen ions and undergo reactions typical of acids with indicators and carbonates. Well, it tells you there what it does. Describe in detail using the information given and your knowledge of the reactions of these liquids. Tests the students should carry out to identify each of the 3 liquids. Now, before you start, you should know that alkenes can be distinguished from alkanes by reacting with bromine water. Bromine water is orange and it decolorizes, it goes colourless with an alkene, but it stays orange with an alkane. So that's how you distinguish between those two. And it already says that butanoic acid is a weak acid and it reacts with carbonates, so you could react it with a carbonate. So those are your 3. Essentially, you're doing 2 tests: testing for an alkene and testing for an acid, and anything that doesn't react like an alkene or doesn't react like an acid is going to be your alkane. Then there's no real test for an alkane, but it would give a negative test for the other 2. So that's the sort of broad outline. What I'm going to do is I'm going to go through the 2 tests, the test for the alkene first of all, and then the test for the acid, and then remember your alkane gives negative tests for both of those 2. So first of all, test for alkene and what you do is you add bromine water. So add bromine water to the liquid. Bromine water is an orange colour, and you shake it, and if it's an alkene, then the solution changes from orange to colourless, and if it's an alkane, it stays orange, but also if it's a carboxylic acid, it stays orange, and that's the key bit to the test. Now, you need to provide some more information about what's actually happening in the test. Now, hexene is C6H12, so it is let's just get this right, 1, 2, 3, 4, 5, 6. It's got a double bond, and it's got 12 hydrogens, like so, and it reacts with Br2, and the Br2 is going to add to the double bond so that that double bond opens up and has 2 bromines on it. So it makes your dibromo alkane. 1, 2, 3, 4, 5, 6. Now this is going to have 2 bromines on, and it's just going to have a single bond because it's now an alkane, and the rest of the hydrogens stay in the same place. So I've gone from a alkene to a dibromo alkane, and you could include any reaction to get the full I think 3 marks for this part, but you do need a reaction in there because it said you should include balanced equations, and if it says you should include, then you need to include them to get the full marks. So you need to show that hexene reacts with bromine to give you your dibromo alkane. So the second test that you can do is the test for the carboxylic acid. Test for carboxylic acid. Now, carboxylic acids are weak acids, and they do act like acids, so they would turn blue litmus red, or they would turn universal indicator red, and you got 1 mark for saying that. But the key thing is, and it says it in the question, that acids react with carbonates to give salt plus water plus carbon dioxide. Now, you know that, and you know, you need to make it clear to the examiner that you know that. So this is Kashoko. So acid plus carbonate gives salt plus water plus carbon dioxide. So you can write down that word equation. Butanoic acid reacts with sodium carbonate to give sodium butanoate plus carbon dioxide plus water. Now the key thing is carbon dioxide is given off when acids react with carbonates, and you see that as fizzing. So you need to say that the reaction fizzes with the acid, but it won't fizz with your alkene or your alkane. So they don't react with the indicator because they're neither acid nor alkali. They're neutral, and they do not fizz. And therefore that's a positive identification for butanoic acid, is that it fizzes when you add the carbonate. Now the word equation you should be able to get to from that: butanoic acid plus sodium carbonate. Sodium butanoate is a little bit tricky. Carboxylic acids give carboxylate salts, so ethanoate you will have come across, plus carbon dioxide plus water. Now in terms of the equation, I doubt if many of you will have been able to write a balanced equation for that, but you may have been able to write a formula equation. So butanoic acid, meth, eth, prop, but. My carboxylate, COOH, H group looks like that. Now it reacts with carbonate plus Na2CO3, sodium carbonate. Now what's going to happen is the hydrogen on the acid is going to be removed and be replaced by sodium, and that's my sodium butanoate. So it goes to give my sodium butanoate, which is just the salt of the acid, C double bond O, O minus Na plus. That's my salt that is formed. So acid plus carbonate gives salt plus CO2 plus H2O. And if you do it like that, that should all be balanced, because what happens is my hydrogen from my acid combines with one of my oxygens from my carbonate to give water, and carbon dioxide is produced as well. That's quite tricky stuff to get the full marks from that, and you know, including that equation, which you need to do because it says up here that you need to do the balanced equation, is quite tricky, but that's your level 8-9 differentiator. Now the last thing you need to do is just say that the alkane, once you've got a positive test for your alkene and a positive test for your carboxylic acid, then the alkane is the material that doesn't give a test for either of the above. Now lots of you put tests for alkanes, burn them. Combustion is the only reaction you know of alkanes. You don't know any other reactions of alkanes, and so it is still a positive test if it's negative for the other two, and that will distinguish your alkane, which was again a little bit tricky. Right, that's it. That's the end of that 6-mark question and the end of the exam paper. If you've got this far and you've got all your green pen marking done, congratulations, well done. Good luck with your revision. Hope it goes well in your exams that are coming up.